The first metal casting process that we're going to go over is the lost foam casting process. And lost foam is an evaporative pattern casting process. So every time we make a pattern and cast it, we lose the pattern itself. The part that we're going to make here is a very simple 2D shape that I have cut out of polystyrene foam. When it's assembled and coated, it looks like this. So this has a refractory coating on it, which helps improve the surface finish. And I've added a gate and runner system. So I have a sprue here, a runner, and a gate where metal will enter the part and fill it. And the molten metal will vaporize this polystyrene foam as it goes. Now, unlike the green sand process, the sand doesn't need to be compactable. What it does need to be able to do is to support the pattern. So I have this round grain sand. If you were to look at this under a microscope, it would look like lots of little beach balls. So it will flow very nicely around the pattern and support it. So I'm going to submerge this pattern into this sand, and I'm going to tap the flask as I fill it with sand, and that'll help all those little granules of sand flow in around it. The last thing I'm going to do is I'm going to put an insulating sleeve on the top of the pouring sprue, and the reason for that is that I want the pouring sprue to be the last piece of metal to solidify. As the workpiece solidifies, as this whole casting solidifies, it's going to shrink. And as it shrinks, it's going to pull in metal from surrounding liquid areas. So by keeping the last area to solidify over here in the sprue, any defects that we get as a result of that shrink will end up in the sprue. And that's the part that we're going to cut off, so we don't really care if that gets some defects. So I'm going to take my flask, and I'm going to gradually add sand. And I'll pause every now and then to tap the flask with this mallet. And that will help the sand flow around the pattern. That's it. That's our completed evaporative pattern casting flask and pattern prepared. I'll carry this into the pouring deck and set it down. And when we go in to pour our castings, this will be the first that we'll pour. The reason for that is that because this is an evaporative pattern casting process, we need a little extra energy to evaporate the pattern itself. So while we pour our castings at about 1450 degrees Fahrenheit, we'll want to pour this one immediately at 450, and then the green sand casting will pour after this one. The metal will have reached probably 350 or 1400, 1350 and 1400. Now the green sand process is a bit more involved than the lost foam process. The reason for that is we need to prepare the mold making media. We need to mix moisture in with the clay coated sand so that it becomes compactable, and we do that in a muller. Now, green sand is the name given to this material only because of its ability to hold moisture. The sand itself is actually black in color. And once the sand is properly mixed, you'll find that it becomes compactable. If we could squeeze it, it will compact and gain strength. This is what makes it able to compress against a pattern and take the shape of that pattern so that we can pour metal against it. Once the sand has been appropriately mulled, then we'll start the process of filling our flask and making our pattern. One of the important characteristics of green sand is its ability to take on moisture and to become compactable. And we have to be able to evaluate that compactability because it's an important part of preparing the media for the mold making process. It's important for us to know how compactable the sand is because too much moisture will lead to gas defects as that added moisture meets the molten metal, and too little moisture, the sand won't be compactable enough, it won't be strong enough to take shape against the pattern plate. So this test is a test of compactability of the sand. I have a standard specimen tube here, a hollow tube filled with loose, uniformly graded sand just out of our muller. And this hammer is going to compress the sand, and then using this ruler, we'll get a percent compactability. So I'll load this in place. 3 rotations of the hammer. And then we can put our ruler in here and see that this is about a 46% compactability. That means that to fill a given volume of our flask, we need to have prepared more than double that volume of loose, uncompacted sand. Okay, now that we've properly mulled our green sand, we can start the process of making our green sand mold. And we're going to go over a number of specialty tools in this process. I'll try to speak the names as clearly as possible because they're important for you to know. But the 3 big ones are the pattern itself, the flask, which of course is in 2 parts, the cope half and the drag half. So we have the cope and drag half which separate. I have these guide pins here that you'll see the pattern will slip down onto. And this is a match plate pattern. It has 2 sides which match one another. And then a lot of the geometry that we talked about in the slide set that you saw. There's a gate and runner system here, a pouring well, the part cavity itself, and a place to locate some cores. So I'm going to start by locating my pattern plate in my flask. The detail goes down. And once I assemble my flask, I can begin the process of filling this with sand. Now when the green sand comes out of the muller, there's lots of chunks and large pieces of somewhat compacted green sand. If we were to load those into the drag half and start ramming up the mold, compressing that sand, there would invariably be some defects that would come along with it. So the first thing we're going to do is use a type of sieve called a riddle, and we're going to load our green sand into this, and this is going to break up all of those chunks that come from what we refer to as heap sand. That is sand that comes right out of the muller. And this riddle will break those chunks up into a fine layer of sand that we refer to as facing sand. So facing sand is always the first layer to go down. All these big chunks that you see here will get broken up in the riddle, and that'll give us a nice clean layer to pick up detail. So here's our first layer, our facing sand. I'm just going to spread it as evenly as I can around the pattern. Maybe pack it down a little bit. Now we're ready to start filling this flask with sand, and we're going to use heap sand at this point. So sand right out of the muller goes into the flask. And now to compact this sand in the flask, we're going to use a tool called a bench rammer. And the bench rammer is just a big wooden hand hammer that we're going to use to compact that sand down. As I mentioned, when the sand becomes compactable, you need a greater volume of loose sand to fill a given volume. That is the volume of the flask in this case. So we will compact it layer by layer, building a strong structure for our mold. Now you'll notice that I compacted the drag side first. And because the drag side is the bottom of the mold, we need to make sure that this surface is flat so that the mold will sit flat. So I have here a treated piece of steel called a strike-off bar. And the strike-off bar is going to let me strike the surface flat. So we'll get the high spots down. Maybe a little bit more work with the bench rammer. And then our drag half is done. So now we can flip over and go to the cope half, which is very similar, but there'll be a few small differences. Okay, after a little bit of cleanup, we're done with the drag half. Now we're ready to flip over and move on to the cope side. So we'll flip this over very carefully. Now, one of the important features on the cope side of the pattern is this marker. This marker indicates where we're going to cut our sprue. That way metal can enter the part cavity. In order to make sure that I know where that is, once we've filled this flask with sand, I'm going to lay my strike-off bar on here, and I'm going to apply some chalk marks. Give me a little crosshair with which to reference when we're done with this half. That's really the only preparation that needs to be done that's different from the drag half of the mold. So just like before, we place the riddle on top of our flask, take some heap sand, and we'll start with a nice clean layer of facing sand on the cope half. Once the facing sand is in, it's back to the heap sand and to our bench rammer. And we continue building the mold layer by layer. Now, even though the cope half, the top surface of the cope half, doesn't sit on the ground, we still want it to be reasonably flat so that when we go to pour the mold, we don't have any bumps or valleys to worry about metal getting into. So again, I'll take my strike off bar here and just scrape the top of the mold clean. Now, one of the things that happens when I strike off the top of this mold is you'll see a little bit of friable sand kind of comes loose on the top. That's going to be important here in a couple of steps when we smooth the top of the mold, but we still have a few more steps to go. Namely, we need to cut that pouring sprue. So my mark's a little faint here, but I can still see it. These were the marks I laid out so that my pouring sprue could be cut with a tool referred to as a pouring sprue cutter. And I will pound that into the cope half until I strike my match plate. Has a little bit of taper on it, so it will actually remove the material quite easily when I pull it out. And then to make sure that we have a nice smooth transition, I have a pouring basin tool. Pouring basin tool does exactly what the name sounds like. And I'm going to press that in there. That provides a nice tapered opening so that as we pour metal, it will it'll funnel in nicely. All right, I ended the last video a little bit shorter because I wanted to find a little bit more appropriately sized pouring basin tool. This is the basin tool that I used. You can see that the pouring basin is not really funnel shaped like we'd like it to be. So this one will give us a much better funnel shape. I mentioned that there was going to be some loose sand on top of the mold, and that's a real problem because if we set this mold up on the pouring deck, some wind could blow that loose sand in, or if we were to miss our pouring basin, we could entrain that sand in. So we have a special tool here that's used to smooth down the top surface of the mold, as well as to help blend in the transition to the pouring basin tool. It's got two ends, a flat, narrow end, and then a rounded end. We refer to this tool as a slick and oval. It's kind of a unique name. But we're going to run this back and forth across the top of the mold. There's some little spots there that we didn't quite ram down as hard as we could have, but the majority is nice and compacted. We'll use the slick and oval to give us a nice clean transition here. On top. That completes the cope half. So now at this point, we can separate our flask halves. You can pull them apart and away from the pattern plate. And what we see is our part cavity right there. Want to be relatively careful not to drop things in. So that is our negative right there. It's actually very clean. The lettering came out very good. Now our finished part has some holes going through it, some through holes. And so on our pattern plate, some little features were made to hold cores. And we mentioned cores a little bit in the slide set. So these cores are going to be placed in there. I have to trim them a little bit because they are made oversized. The features that are made by the pattern here on the ends of the part that give us a place to locate our cores are called core prints. I'll also make sure that there's no obstructions here in our pouring sprue with the slick and oval. Just use that to kind of clean out the pouring sprue that we made. Okay. Now that our cores are placed, we can reassemble our mold. And now it's ready to go into the pouring area where we can start melting some metal and getting ready to pour. Now that the molds have been made, we've brought them into the pouring deck, and we've got to take a couple more precautions as we stage them before we can actually melt metal and pour. The first precaution is that when we pour metal into these molds, that metal is going to want to lift anything that's buoyant around it. So for the lost foam mold, this insulating sleeve that I talked about is going to fill with metal. Because the sleeve is so light, that will give it a tendency to lift when the metal gets inside. So I've added a couple pieces of ballast here, these two pieces of steel, to hold that insulating sleeve down so that it doesn't lift off when it fills with metal. And the same thing here, I've clamped the two flask halves of the mold together. The reason for that is, if you think about it, if we filled this mold cavity with metal and the amount of metal above the parting line weighed more than the sand in the cope half, then the cope half would become buoyant and it would lift, and then the metal would jet out of the parting line. That probably wouldn't happen here, but it's a standard safety precaution that we're going to take. As well, when we fill this green sand mold with metal, the hot metal is going to drive back a layer of water vapor as it evaporates the moisture that's closest to the part cavity. And when that moisture starts to pass through the permeable molding media, we want to give it lots of opportunities to off-gas and to escape. So underneath the green sand mold, you'll see that I've added this perforated bottoming board. And the bottoming board just serves to keep the mold off the concrete so that that moisture can escape. The last thing you'll see over here on the right is an ingot tray. We're going to add a little bit of extra metal to our charge in the crucible, and that makes sure we have enough material. Once we're done pouring these, we're going to pour off the excess. So the order of the pour is going to be the lost foam mold at 1450. Remember, we needed that extra temperature to vaporize the polystyrene foam pattern. Then we'll move on to the green sand mold. By then, the metal will probably have cooled off a little bit to 1400 degrees Fahrenheit or just below. And then once we've filled this mold, we'll pour off the excess. After we give it 20 or 30 minutes for things to cool and solidify, we'll unmold and remove our castings. We have to take some precautions as well over here at our gas-fired furnace. We have our crucible here, which is a refractory material, and we filled this with some cuttings and trimmings of aluminum, as well as some pre-melted aluminum alloy. And just like in the welding lab, anytime we get this metal to an elevated temperature, we want to protect it from the oxidizing elements of the air. And so I have here a powdered flux, and this is really not that much different from the flux that was on the electrodes that we welded with in last week's lab. I'll add that flux and kind of make sure it goes to the bottom of the melt. I'll close this furnace and turn on, ignite the gas. Flow of air, compressed air, and natural gas is going to swirl inside here. It's going to heat up that crucible and get us up to our necessary melting temperature. Once we're at our melting temperature, I'm going to bring a skimming tool down, and the skimming tool is going to scrape off any impurities that the flux brings to the surface. And then once the melt has been properly skimmed, we'll be ready to pour. All right, now we'll start our gas-fired furnace. All right. Okay, now that we've skimmed off the dross that comes to the top of the melt, that's the result of the flux that we added. Now we're going to use a pair of tongs to take the crucible out of the furnace. We'll slowly lower these around. All right, why don't you grab that? Grab a shield. I'll hold this. All right, so now we'll pick up the crucible, lower it into the stretcher all the way down. Okay, pick the tongs up. All right, lift and slowly lower the clamp. Okay, we're going to pour the lost foam first. There's going to be a little bit of a belch right as we first pour, as some of that polystyrene foam becomes vaporized. All right, now we'll come to the green sand. And then lastly, we'll pour off into our ingot trays. All right, back to base. And then we will reverse the order. Up. Okay. Very good work. Okay, we've just poured these castings about 20 seconds ago. And so this is when we want to notice the effectiveness of the insulating sleeve. So here's the lost foam casting, and you can see that the oxide layer is formed on the top of the aluminum, but that insulating sleeve is keeping that completely liquid. Move on to the green sand casting. The first thing you'll notice is that what was once a flat surface is now concave. It's a little bit mushy in the middle, but it's somewhat solidified. That's that aluminum shrinking as it cools. And then lastly is the ingot, and this ingot has now solidified completely. It's chilled by the steel. So there's 3 different examples of the insulating properties of these different materials. In about 25 minutes, we'll be able to unearth these castings. We'll take a look at them as we take them out of the mold, and we'll get them cleaned up and look at each one individually. Okay, so our castings have solidified now for about 20 minutes. I can tap on even the insulated sleeve, which will be the last part to solidify. And everything is solid, so I'll remove the little weights that I put on here. And the first one to take out will be the lost foam casting. Now before I quench this, if you look carefully, you'll see that once I brush that refractory coating off, you can see the aluminum, and the surface finish is so good that you can still make out the little pellets of polystyrene foam. So it's a high resolution casting process and has a lot of advantages over the green sand process. We'll get that cooled off a little bit. And that can move on to being sectioned. I'll set that aside so that we can take the green sand casting out. I'll remove my clamps. And the first thing you'll notice is that our cores are a little bit discolored after they've been exposed to the metal. But here I'll use the bench rammer to knock our casting out. And now that it's out, before I quench it, you can see the completed gate and runner system. You can see where the pouring sprue was attached. And once this has been cooled, I'll clean our core material out. But here you can see that the cores made through holes in the sides of the part. And that's the purpose of those cores, is to generate the type of geometry that you can't make with a traditional cope and drag style mold. So So I'll get these cooled off, and then we'll move on to sectioning these, and we'll take a look at the finished castings. All right, as we wrap up this activity, we're just going to look at the castings that we made. The lost foam casting wound up having a really excellent duplication of the surface finish from our original part. There are a few defects that we see here, mostly around the hole in the middle. That's because when we cut a hole in the polystyrene foam, we used a twist drill, and it tended to tear out some of the pellets of polystyrene foam. I wanted to show you a consumer product that's made by polystyrene foam. This is a pipe fitting, and it's cast iron. It's made by the same process, and you can definitely see a better surface finish here. That's because the patterns for consumer products would be made in their own mold, and that would yield a better surface finish on the foam pattern in the first place, which would ultimately give you a better finish on the casting itself. If you think back to the picture of the engine block that we talked about in the slide set, that was General Motors 5-cylinder, and if you know anybody with a first generation Chevy Colorado or GMC Canyon and they keep their engine really clean, have them pop the hood and you'll still see the pellets from when that engine block started as a polystyrene pattern. The green sand casting itself also has some defects in it. There is a small shrink defect here. The result of that is that the gate, if you look on the pattern, how small the gate is, that froze off before the casting itself had completely solidified, which means that as the casting cooled, it couldn't draw in liquid metal from anywhere else, like in the pouring well or the riser. And so that created a defect in the part. We avoided that in the lost foam casting with that big heavy runner system. So it just so happens that this pattern is used here at Western for research in shrink defects. So this gate and runner system is actually replaceable to turn that defect on and off. But we see really good surface finish here on the inside of our cord sections, and that's exactly what you would get on the inside of your engine blocks and cylinder heads when the green sand system is used to make those types of products.